Welcome to the deep dive. We take the latest, densest findings from the scientific frontier and turn them into knowledge you can actually use. Today, we are strapping in for a journey to the deepest cosmos to talk about black holes. But specifically, we're discussing how these ultimate gravitational voids can actually have children. We're talking about cosmic progeny.
That's right. Our stack today centers on what we can really only describe as gravitational birth announcements, delivered by the LIGO-Virgo-KAGRA Collaboration. Our focus is on two recent, highly unusual gravitational wave events detected late last year, in 2024, GW241011 and GW241110. Okay, let's unpack this. Our mission is clear. We want to understand what makes these two signals, special enough to suggest the existence of second-generation black holes.
And we also need to explore how the incredible precision of these events allowed scientists to confirm Einstein's predictions with, stunning accuracy, while also challenging the very edges of fundamental particle physics.
Right. So just to set the stage for you, remember that gravitational waves are literal ripples in space-time itself. They're caused by the most violent events out there, usually the merger of two black holes. And the LVK network analyzes the characteristics of these ripples, the frequency, the amplitude, all that stuff, to reconstruct every detail of the collision, the mass, the distance, and critically for today, the rotation or spin of the objects involved.
And this network, the LVK, it's wrapping up its fourth observing run, 04. They've captured hundreds of these mergers already, which gives them a massive baseline for what's, normal. But these two new events, they stood out immediately. Primarily because of those peculiar spins.
Yeah, the data from these two events it kind of defies the standard astrophysical formation models we usually work with. Let's start with GW241011, detected back in October 2024. It happened about 700 million light years away. The merger involved two black holes, approximately 17 and 7 times the mass of our sun.
Okay, so one nearly double the size of the other. What was the critical detail about the larger one then?
The spin. The 17 solar mass black hole was measured to be one of the fastest rotating black holes observed, since the detectors began operating. If you were to calculate the maximum spin rate that physics allows, this thing was right up against that limit. That rapid near maximum rotation is like the first key fingerprint here.
Wow. That's already intense. But then we got GW241110 detected just a month later, but coming from much further out, 2.4 billion light years away. That distance alone is just staggering. So what did that event involving roughly 16 and 8 solar masses show us about spin?
Well, it introduced a totally different kind of strangeness. Here, the primary black hole, the bigger one, was found to be spinning in a direction opposite its orbital path. The researchers actually called this a first-of-its-kind observation. So imagine the system is orbiting, say, counterclockwise, but the black hole itself is spinning clockwise. That's this retrograde motion.
That's truly wild. Okay, so we have one merger with extreme rotation and another with completely misaligned, actually retrograde rotation. And crucially, in both cases, you have this significant mass ratio. The larger object is roughly twice the size of the smaller one. Why do those specific measurements, the mass ratios and these, frankly, bizarre spin orientations, matter so much? How do they act as fingerprints, and what standard theory are they defying?
They matter because they basically contradict the simplest, most common way we think black holes form and pair up. Typically, black holes form in, isolated binary pairs. They're born from two massive stars that lived and died together. When this happens, their spins and their orbital paths are usually pretty well aligned. This typically results in a merger remnant that doesn't spin very fast because they've been kind of tidally locked and synchronized for maybe millions or billions of years.
Right, so the standard model assumes these two objects are marching neatly in the same direction, almost like synchronized swimmers.
Exactly. But these new observations, they suggest a much more violent, multi-step history, an origin not in isolation, but in, utter chaos. The high spin of 241111 and the misaligned spin of 241110, you combine that with the large mass differential, those are the precise calling cards of multi-generational formation. They are, I think, the most direct evidence we've seen that these black holes were actually formed from previous mergers. Okay, this brings us right to the core concept, the second-generation black hole, or 2GBH. If the spins prove it, let's define it really clearly for everyone listening. What does it actually mean to be a 2G black hole? It's sort of the cosmic equivalent of a remnant, but a remnant of a previous collision. The black hole that is the result of an earlier coalescence. So you have two first-generation black holes may be formed from stars they merge, releasing a huge amount of gravitational energy. The resulting single larger black hole, that is the 2G component. And because that initial collision was likely pretty high energy and probably asymmetrical, This new, larger remnant often inherits exactly the kind of high or, unusual spin characteristics that we just saw in this O4 data.
And this process is called a hierarchical merger. Okay, so this tells us the environment is just as important as the physics, right? This isn't just something that happens anywhere out in the void.
Oh, absolutely.
Yeah.
It requires extraordinary conditions. These hierarchical systems, they seem to form only in extremely dense cosmic environments. The most common candidates are things like globular star clusters. These clusters are ancient, incredibly crowded places packed with millions of stars and, as a result, packed with lots and lots of black holes.
So instead of two lonely black holes orbiting quietly for eons, we are talking about a gravitational mosh pit where objects are constantly interacting, bumping into each other.
That's a perfect description, yeah. In these dense, dynamic crowds, black holes are far more likely to experience close gravitational encounters. They can get kicked into new orbits or, run into each other and merge again and again. The collaboration put it really beautifully, I thought. They noted that these systems teach us that some black holes exist not just as isolated partners, but likely as members of a dense and dynamic crowd. It's like gravitational pinball, but on the scale of entire star clusters over cosmic time.
It's amazing to think of the level of violence and just sheer randomness required for that black hole, the one 2.4 billion light years away, to end up spinning backwards, purely because it was repeatedly knocked around and merged in some crowded neighborhood before finding its final partner.
Exactly. And while we'd seen prior compelling evidence suggesting this process, like, some of the really heavy masses involved in earlier detections like GW190521, these two new events provide, I'd say, the most direct, unequivocal observational evidence yet for this hierarchical merger pathway. We are literally watching black hole families grow.
Huh. What are the statistical implications now that this formation path seems, well, validated?
Well, the projections are pretty significant. Theoretical modeling suggests that if this dynamic formation pathway in dense star clusters is a common mechanism, and it seems like it might be, then maybe up to about 10% of all detected binary black hole mergers could involve at least one 2G component. And naturally, if you have 2G, the possibility exists for 3G, third generation, and maybe even 4G black holes to form if the remnant survives long enough in that cluster to encounter another merger candidate. We've really opened a new chapter on cosmic genealogy here.
Wow. We've moved beyond simply cataloging black holes to actually constructing a verifiable family tree for these, the darkest, most mysterious objects in the universe. That's a staggering achievement. Now, okay, beyond solving the mystery of black hole parentage, the immense precision of the GW241011 signal, specifically because of that incredibly rapid rotation, allowed the collaboration to pivot and use it as a testing ground for fundamental physics.
That's the dual importance of these discoveries, absolutely. These extreme mergers function as an invaluable laboratory, as they put it, for probing the fundamental laws of physics. We are putting general relativity to the test under the most extreme high-gravity, high-velocity conditions imaginable. Okay, let's look at test one. Einstein and Kerr, what specific prediction were they aiming to verify with that rapidly spinning object? So they were testing the mathematics of rotating black holes. General relativity, Einstein's theory, predicts that all black holes are actually defined only by their mass and their spin. That's it. Back in the 1960s, the mathematician Roy Kerr developed the exact mathematical solution describing a rotating black hole. We call this the Kerr metric.
And that rapidly spinning 17 solar mass black hole in GW241011 gave them the perfect data point to test it.
It really did. Because a rapidly rotating black hole, it slightly deforms the space-time around it. It kind of frame drags space-time with it. The faster the rotation, the stronger the effect. This deformation or distortion, it leaves a characteristic measurable fingerprint in the gravitational waves emitted during the final moments of the merger. You can literally see the effect of the spin in the wave pattern.
And after analyzing that fingerprint against the Kerr solution, what was the verdict on Einstein's theory? Did it hold up?
Excellent agreement. Yeah, they verified Einstein's prediction with what the collaboration explicitly called unprecedented accuracy. Every time we find an event this extreme, right at the theoretical edge, and Einstein's framework holds up, it just solidifies our foundational understanding of gravity. It's quite remarkable.
That's seriously impressive. But you also mentioned a second test linked directly to the mass difference, the 17 and 7 solar masses, something you called a cosmic hum. What was test 2?
Ah, yes. Test 2 involved detecting what are called higher harmonics, or sometimes overtones. Normally, when two roughly equal mass black holes merge, the gravitational waves emitted are dominated by the fundamental frequency, the main ring-down tone. However, because the two merging objects in GW241011 had significantly different masses, The system was highly asymmetrical. It wasn't a balanced collision.
Okay, so if the geometry is asymmetrical, then the resulting space-time oscillation patterns must be far more complex than a clean, symmetrical collision would produce.
Precisely. That asymmetry generates higher frequency overtones in the gravitational wave signal. Think of it like the subtle, complex high notes you hear when a musical instrument is played. It's not just the fundamental note, it's the higher harmonics that give it richness, its timbre. Detecting this higher harmonic, this hum, requires immense detector sensitivity because it's usually much fainter than the main signal. For GW241011, this phenomenon was observed with superb clarity, and it was only the third time ever it had been clearly seen. So again, it confirms another very subtle prediction of general relativity.
So Einstein is looking pretty secure, but you noted that this data simultaneously helps us search for physics beyond the standard model. How does measuring the rapid rotation of a black hole help us hunt for, well, hypothetical particles?
Right, this is where the particle physics application comes in. And it's perhaps the most surprising application for many people.
Yeah.
We use the rapid rotation of black holes, like the one in GW241011, to search for hypothetical particles known as ultralight bosons. These are particles predicted by certain theories that go beyond our current standard model of particle physics, specifically theories trying to address things like the nature of dark matter or maybe high-energy interactions we don't understand yet.
Okay, and what would these elusive bosons actually do to a black hole if they were present in the universe?
Well, the theory goes that if their mass falls within a certain, very specific theoretical range, they would interact dramatically with the black hole's rotational energy. These bosons would basically form a massive cloud around the spinning black hole, kind of extracting energy from it through a process called superradiance. This cloud formation, sometimes people call it black hole hair, although that's a bit debated, would actively extract rotational energy. It would cause the black hole spin to slow down dramatically over cosmic time, millions or billions of years.
Ah, okay. So the existence of a massive ultralight boson in the right mass range would effectively act like a brake, slowing the black hole's spin over time. Since we observed that the massive black hole in GW241011 continues to rotate rapidly near its theoretical maximum, even after presumably existing for a long time, what does that imply for these hypothetical particles?
It implies that they probably don't exist within that specific mass range. It means we can rule out a wide swath of possible masses for those theoretical ultralight bosons. The fact that the spin hasn't been significantly depleted is direct observational evidence constraining those theories. If these particles exist, they must fall outside the mass range that would interact strongly with the 17 solar mass black hole. So these astrophysical discoveries are simultaneously refining our understanding of gravity and providing critical constraints for particle physics experiments happening right here on Earth. It's pretty amazing synergy.
What a convergence of discovery. Okay, so we've traced black hole genealogy through the chaos of dense star clusters, validating the formation path of hierarchical mergers. That's huge. And we use those very same chaotic signals to verify core predictions of general relativity with unprecedented accuracy, all while simultaneously conducting, effectively, a large-scale experiment to eliminate candidates for new elementary particles.
That synergy between astrophysical observation and fundamental theoretical physics is really the true hallmark of this kind of work. It just underscores the immense value of the international LVK collaboration and the relentless pursuit of increasing the sensitivity and precision of these incredible detectors. And the data is only going to get better, allowing us to detect even more subtle harmonics and finer details in the future.
Absolutely. And as we wrap up this deep dive, maybe consider this provocative thought for your week. If a black hole is confirmed to be the child of a previous merger, and theoretical models predict even 3G and 4G generations might exist.
Well, what does it mean for the structure of our universe if the most violent objects in space are actually a part of a multi-generational family tree, growing denser and heavier with every single collision?
Yeah, it forces us to rethink cosmic evolution on a massive scale, doesn't it? If black hole families are a primary mechanism for mass growth in these dense regions, it dramatically shifts our understanding of how structure actually forms and evolves over billions and billions of years. A powerful thought to chew on indeed. Thank you for joining us for the deep dive. We'll catch you next time.